So today's topic is going to be plate tectonics because this is one of those absolutely vital concepts to understand in geology because it affects so many different aspects of the planet. And I know you've gone over this already, or should have gone over it in physical geology, but when it comes to really important concepts, it's a good idea to have a review just to make sure that you understand what's happening. And in order to understand plate tectonics, we actually have to take a look at the structure of our planet. And there's two ways of looking at Earth's structure. One way is the classical view, and this is where we look at the composition of the different layers of our planet. And the other way is the geophysical view, which is where we look at the state of matter inside our planet. Let's look at the classical view first. So we have three layers in the classical view. The outermost one is the crust. And the crust is 3 to 70 kilometers thick. The density varies from about 2.5 to 3 grams per cubic centimeter, and it's made from granite or basalt. The continents are made from granite. They are thicker, on average around 40 kilometers thick, although it gets up to the 70 or more kilometers thick in big mountain ranges. The ocean crust is made from basalt. That's thinner. That's usually like 3 to 7 kilometers thick. And the basalt is denser. Underneath the crust, we have the mantle. This is a lot thicker, up to about 2,900 kilometers thick. It is denser, and it is made predominantly of the rock peridotite. And then the center of our planet is the core. You can see this is quite dense. I put 11 grams per cubic centimeter, but it does actually vary whether you're at the absolute center or towards the edges of the core. It's made from mostly iron and nickel. So that's our basic classical subdivisions. Now, to understand plate tectonics, we have to take a look at the geophysical subdivisions of the Earth, where we're looking at the state of matter. We live on the lithosphere, the outermost part of Earth, and that's 5 to 250 kilometers thick, so that's going to include all of the crust and then part of the uppermost mantle. It is a rigid solid. Underneath the lithosphere, we have the asthenosphere. And this goes from the base of the lithosphere to 660 kilometers deep. It always ends somewhere right around 660. And it's plastic, meaning it's kind of squishy. It's not a liquid. It's not a rigid solid. It's a kind of like gooey plastic like the center of an Oreo. That's important because if it was not plastic, if it was rigid, we would not have plate tectonics. The only reason why the plates can move around is because that's kind of this squishy plastic material. Now underneath that we have the mesosphere, which is another solid layer. And then we get the outer core, which is liquid. Again, it's important that that's liquid. That's what generates our electrical, our magnetic field actually, because the flowing metals create an electrical field which generates the magnetic field of Earth. And then the absolute center part of the planet is solid. And we can see that on this diagram. We're comparing the crust, mantle, core of the classic subdivisions to the lithosphere, asthenosphere, and so on of those geophysical subdivisions. So this is just comparing those two different perspectives of the Earth. All right, so plate tectonics. Plate tectonics states that Earth's lithosphere is broken into pieces. Those are the plates that move over the plastic asthenosphere, and when they move, they cause earthquakes and volcanoes and mountains and all kinds of other geologic processes to occur. So basically that outermost shell of the Earth, the lithosphere, is broken up and it's constantly moving around. How fast does it move? Usually only a few centimeters every year, about as fast as fingernails grow. All right, now since these plates are moving around, they're going to interact with each other. And that's what we're going to look at next, is how do these plates interact with each other and what happens. We're going to start with a divergent plate boundary. Divergent means plates are moving away from each other. And if this happens on the continents, we get what's called a continental rift. And ultimately, this is how continents break apart. You get this rift developing, breaking pieces of the continents away from each other. In this case, the lithosphere thins, because as they move away from each other, the lithosphere gets thinner and thinner, and this causes volcanoes to occur, and this causes earthquakes. If you want to go to a place where this is happening today, go to East Africa. The East African Rift is where the easternmost part of Africa is breaking away from the rest of the African continent. If this movement, this divergent movement continues, eventually you can get a mid-ocean ridge, which is this mountain range that's in the middle of all the ocean basins. This is where new ocean crust forms. You get volcanic activity and you get earthquakes. So what you usually see happening is a sequence where we have our rift begin to develop. Notice those purple arrows showing that we're moving away from each other, right? Moving apart at that location. When this occurs, a valley develops. That's the Rift Valley, where the lithosphere has thinned. As this spreading apart continues, you'll eventually get this kind of long, narrow sea, like the Red Sea today. And if that movement then continues even more, you get the big ocean basin with the mid-ocean ridge in it. And that's the progression we see. So for instance, when Pangaea, a supercontinent that existed, 300 million years ago or so, when that broke apart and South America and Africa broke apart, for a while there was this narrow sea separating them before it grew larger and larger into the Atlantic Ocean that we know today. All right. Well, plates don't only have to move away from each other, they can also slide alongside each other. And that is a transform plate boundary. There's no subduction here, there's not spreading apart, so you're not going to get any volcanic activity at these kinds of boundaries, but you do get earthquakes. And the classic example of a transform plate boundary is the San Andreas Fault. So what we see here in blue, that's the Pacific plate. In green, that's the North American plate. There's the San Andreas Fault that separates those two, right? And we don't get a lot of volcanic activity right there, but we do get frequent earthquakes. And eventually what's going to happen is San Francisco is going to move this way because it's sitting on North America. LA is going to move up this way because it's on the Pacific plate. And eventually they will join as those two plates slide alongside each other. Now the last thing that can happen when plates interact is they can push against each other. And that's a convergent plate boundary. And in this circumstance, you could have an ocean plate meeting a continent. And if this occurs, you get subduction. So subduction is where the ocean plate, because it is denser, will sink underneath the continental plate. And I wrote the subducted plate melts. It's actually part of the subducted plate, and the mantle above it will begin melting. If we get this melting happening, we get volcanoes. And we also get earthquakes. And that's what we're seeing right here. We have this ocean plate sinking underneath the continent. We get this melting occurring, creating those volcanic mountain ranges. This is happening off the west coast of South America today, creating the Andes. It's also happening off the west coast of Washington and Oregon, creating the Cascades. You could also have two ocean plates colliding with each other. In this case, subduction occurs. And which plate's going to end up subducting? Well, it's going to be the denser plate, right? Density drives this. So whichever of the ocean plates is denser will subduct, and usually it is the older, colder plate that's going to be denser. It subducts. Again, it gets to a certain depth where part of the plate and the mantle above it begin melting, and thus we get volcanic activity and earthquakes. And that's what we see here. Two different ocean plates. We get the subduction occurring. A good example of where this is happening today would be, say, Japan, creating the Japanese islands. Now, the last thing that can happen where two plates collide with each other is you could have two continents colliding. Continental crust is very thick. It's also very low density, so it cannot subduct. Thus, instead of having one plate sink under the other, the two plates crash against each other and crumple, and the crust thickens. This is where we get the thickest continental crust. You get a lot of earthquakes occurring in these areas, and you can also have what's called a suture zone form, where, for instance, two continents collide and then get stuck together. That's the suture zone, where they get stuck together. A great example of this is where India has collided with Asia. So if we could go back in time, we'd have India, we'd have Asia here. There was a subduction zone there, but this continent was basically kind of being carried closer and closer and closer to Asia. And then eventually it slammed into Asia, creating the Himalayan mountains and this area of this very thickened continental crust. So these are the plates that we have today. And hopefully you can notice that they come in different sizes. Some are very big, some are relatively small, some are almost entirely ocean crust, some are a mix of continental and ocean crust, some are entirely continental, and they are all constantly moving and interacting with each other, creating these mountains and volcanoes and other things. Now, we are studying historical geology. And so we need to be able to look at the rocks that exist and basically interpret how they formed and how they got to where they are. And there are certain clues you can find in rocks to help you interpret the ancient plate tectonics that were happening. And so there are some rocks that are unique of where a continent and an ocean plate were converging, right? And one of the things you'll see there, you'll see an accretionary prism or an accretionary wedge. And this forms where you have that one plate subducting. There's going to end up being these sediments and little bits of the ocean crust that get scraped off the subducting plate and added to the continent. Now, because of the forces involved, these are often going to be deformed and they're going to be metamorphosed. But basically that accretionary wedge is this stuff that's scraped off that subducting plate. And some of the rocks you might end up seeing include something we call a mélange. And these are very complexly deformed. And in fact, this is a mélange right here. And you notice how we don't have any distinct beds, right? These were sedimentary rocks, which means we should be seeing these nice layers in there. But because of the forces involved in this subduction and when it got scraped up, things get very, very deformed, very metamorphosed and kind of churned up. And so we no longer see those nice layers of sediment. We just see this very kind of ground up rock right there. And that's our mélange, and that's very typical. It's usually part of the accretionary wedge. Now, other unique things that we'll find are things called an ophiolite suite. An ophiolite is this distinctive, these distinctive layers of rock that are a piece of the abducted ocean crust. Abducted, not abducted. We are not kidnapping the ocean crust. What abduction means, Well, subduction is when the ocean sinks, right? The ocean crust sinks under the continent. Abduction is where a piece of that gets caught and added to the continent. So it gets kind of scraped up and added in there. And it has a distinctive layering to it, where you have ocean sediments, followed by pillow basalts, followed by sheeted dikes, followed by gabbros, and then you'll see these periddotites. And what you're looking at, ocean sediments, there's lava that erupted on the ocean floor, that's why it has pillows. Then these dikes are basically the conduit where the lava was carried from the magma chamber to the ocean floor to erupt. That's what the dikes are. The gabbro is the magma chamber. So that's where we had this ancient magma chamber. The dikes are where the magma rose to the ocean floor. The pillow basalts are where it erupted on the ocean floor. And then underneath it all, well, periodotite, I just told you periodotite is what makes up the mantle. This is actually ancient mantle rock that got kind of scraped up and abducted and added to the continent. So you'll often see these ophiolite suites where we're dealing with these ancient ocean continent convergence. You will also see a special type of rock called blue schists. I happen to love blue schists because they really are kind of a blue and purple color, and that's because they have a special mineral in them called glaucophane that's just a brilliant blue-purple. Blue schists are high-pressure, low-temperature metamorphic rocks, and these only form in subduction zones. The reason they only form in subduction zones is because when we have that plate get subducted, right, it's been sitting under the ocean for a long time, so it's really, really cold. It takes a really long time to heat up. That's why we have low temperature. But that plate sinks deep into the asthenosphere. And the deeper we go, the higher pressure it is. So we get high pressures, but low temperatures. And that is unique to a subduction zone. So where you see blue schists, you know you had subduction there in the past. Okay, so that's one thing that's important to recognize in plate tectonics. Some of these rocks that can tell us how the continents have moved around in the past and what kind of plate boundaries we had in the past. But another important thing to go over is the Wilson cycle, because this happens over and over in Earth's history. This is the opening and closing of an ocean basin. So in physical geology, you probably learned about the supercontinent Pangaea. You should have learned about that. And a common misconception is that Pangaea was the only supercontinent, when in reality there have been many of these. So basically, over geologic time, what happens is all the continents basically slam together, form a supercontinent, then they all kind of split apart, and then they all come back together, and then they all split apart, and this happens over and over again. Well, part of this is the Wilson cycle. So we have our continents all together, where they're going to have to break apart and create an ocean basin. So we're going to have a new ocean basin open as the continents split apart, and then eventually it's going to close back up as the continents come back together. So in the Wilson cycle, we begin with some development of rift systems, right? It says complex system, linear rift valleys on continents. This is like the East African rift today. So we're starting to get a continent beginning to split apart, and we'll see a rift valley. And then as the splitting continues, we get this narrow sea forming, like the Red Sea today. Then as this continues, it is going to split apart into forming a big ocean basin, like the Atlantic Ocean today. And then eventually that ocean crust that makes up that ocean is going to cool down and become dense enough that it starts subducting. And so then we're going to start having the continents get closer together, and this is like the Pacific Ocean today, where there's subduction happening. Then that ocean is going to close up and get narrower and narrower and narrower, and like what we have in the Mediterranean Sea today, and then eventually the continents will collide together again, like what happened in the Himalayan mountains. So we see this over and over in Earth history, where a rift valley forms, a narrow sea forms, a big ocean forms, then subduction begins, the ocean starts going away, continents collide, new big supercontinent formed, then eventually they split apart, and then come back together, and we're going to see that several times in Earth's history.